Hello and good morning. This is problem session number 7, lecture 27 of chapter 3. We are going to solve problems 3, 27, 28, 29 and probably 330. In 327 you have a parallel plate capacitor. The separation is D, the width is W, right? The surface area is A. Initially, the space between the two plates is filled with a conductor or with a dielectric of relative permittivity, say epsilon r, and you charge it under a potential difference V0 in order to have a charge Q0 on the upper plate minus Q0 on the lower one. After being charged, you disconnect it from the battery and you pull the dielectric slab to this position where only a part of it of length x is still between the plates, and the other one, which is that one, this one should be L minus x, because originally the length of the slab is the length of the capacitor itself. Now, having reached this new position, the question is, what is the electric force between the dielectric slab and the capacitor? Okay. Now, if you look at this is now, after pulling the dielectric slab, that region here between the plates is similar to two different capacitors, one of them of length x, separation D, and with a dielectric between the plates, another one with a length L minus x, which is this amount or that amount, separation D, but with air being the dielectric. Those two capacitors, the dielectric one and the air one, are connected under the same potential difference, which is V0 up and 0 down for both. Two capacitors connected under the same potential difference means that they are in parallel. And for parallel capacitors, we have 1 over C equivalent C equivalent equals to C1 plus C2. Okay? No, now C equivalent of both capacitors in this region, the dielectric one and the air one, is C1 is the capacitance of the dielectric capacitor, which is this one. It is epsilon, which is epsilon 0, epsilon r, times the area. Now the area is this one, okay? It is W times X over the separation epsilon A over D. This is the first that is the first capacitance of the first capacitor, which is the dielectric one. Okay. Now plus the second one, it is this capacitor, the air one, which is epsilon 0 times L minus X, right? This one times W, that's the area, over same separation. So if you want, this is an epsilon 0 over D into epsilon r Wx plus Lx plus L minus X times W. That is C equivalent. Okay. Now we want to find the force. One very quick method of finding the force in such a case, as we have done it in the course, it is by applying the relation between the force of energy and energy, F equal minus grad of W. Now, after disconnecting the battery or disconnecting the capacitor from the battery, you are preserving the charge on the upper and the lower scale, upper and lower plate. So this is minus gradient of what? Gradient of the energy. The energy of the capacitor, the easiest one to choose here is half Q square over C, like this. and that is equal to minus grad, okay, half q square is a constant, so you can take it outside the integral sign, half q, the derivative sign, sorry, half q square, of the gradient of 1 over c, with respect to what? With respect to whatever x here, with respect to x, that direction. So this will be the partial derivative with respect to x, okay, and there is a minus sign outside, and this is in the x direction, of 1 over c. That is c equivalent, so this is 1 over c equivalent. You find 1 over c equivalent, then you derive it with respect to x to obtain the force between the dielectric slab and the capacitor. And if you do the calculations, you will have to obtain something like ax here times v0 squared w over 2d epsilon minus epsilon 0. Okay, so now here we have replaced q and v, we have put q in terms of v0, the initial potential difference under which the capacitor was charged. Okay, so that is 327. In 328, the upper and the lower conducting plates of a large parallel plate capacitor are separated by a distance d, that is the distance t. This is the upper plate held at a potential v0, and that's the lower one held grounded, v equals to v0. Okay, a dielectric slab of dielectric constant 6, this one, is placed on the lower plate like this. Its thickness is 0.8 d. Now that upper part, which is still air, is now of thickness what? The remaining part, 0.2 d. Okay? Fine. Determine the following by solving Laplace equation. The potential and the electric field in the dielectric slab here, and B, the potential and the electric field in the airspace there, and the surface charge densities at the lower and the upper plates. Okay. Now, the mathematical calculations should be the last step when you solve a physics problem. First of all, you have to read the question, as I did. Understand it, number 2. Number 3, draw the figure with all the given on it. And then think, what is this problem about? You are asked to find the potential here and there, and you are given the boundary conditions. So this is number 1, a boundary value problem, number 1. Number 2, which system of coordinates do I use here? The figure suggests Cartesian coordinates. That's number 2. Number 3, you have symmetry with respect to x and z, and you have only variations with respect to y. Okay? So you have to apply Poisson's or Laplace equation, solve it in Cartesian coordinate with y variable only. Number 4, because we have only variations with y, and because nothing is mentioned about any volume charge density here or there, so we have to solve Laplace's equation and not Poisson's equation. So Laplace's equation, after reading, drawing the figure, putting the given, know what the problem is about, make a plan as how to solve the problem, then you start writing and solving. Okay? So we have to solve what? Laplace's equation is equal to 0. The Laplacian of v is 0. And you have two regions here. Region 1 here and region 2 in the air up there. So you have to solve this. Laplacian of v in 1 is 0, and Laplacian of v in 2 also is 0, because you have two different media. Okay, now the Laplacian Cartesian coordinates with symmetry in z and x, this will leave me with d square v by dy square equals to 0. It means that v is equal, first dv by dy is c1, means that V is equal C1y plus C2. That is in region 1, let's say. In region 2, a similar solution but with different constants. So you can say C3y plus C4. Okay? So we have solved Laplace's equation in both media. We obtained this is the solution now, but it's not a unique one. We have to benefit from the boundary conditions. Okay? In order to use the boundary conditions, we have to know, here we have 1, 2, 3, 4 constants of integration. Therefore, we need 4 conditions in order to find these 4 constants. What are these conditions? The first condition is that V at y equals to 0, V at y equals to 0 is 0. Y equals to 0 is in region 1, so we take this one. That should be 0 when y is 0. So C1 times 0 plus C2. This means that C2 is 0. Okay? Then, again, second condition, V at y equal D is V0. What does that mean? V at y equal D, we are in air, so we are in the second one. So this is V0 now, equal C3 times D plus C4. This is a relation between C3 and C4, and that C2 is 0. Okay? We still need two boundary conditions in order to find what? To find the 2 remaining constants of integration. Now, for that, you have to apply 2 other boundary conditions. One for the, and these should be applied here at the boundary between the 2 media. Since we have here, the charge which we have here is 2 types. Free charge on the upper and the lower plates, number 1. And probably, because this is a dielectric, we can have a polarized charge on the surface or in the volume. But if you try to find the displacement vector D, as you know, the displacement vector D depends on what? Depends only on the free charges. As you know that the electric field between the plates of a capacitor E is rho s over epsilon or epsilon 0. Epsilon E is D. This means that that expression of E will be in a dielectric D equal rho s. Okay? D equals to rho s. Now here you have V and V. From this V and that V you can find the electric field. Electric field in 1 is minus grad V1. Electric field in 2 minus grad V2. Having found the fields in 1 and 2, you multiply the field here by epsilon 0, right? To find what? To find D. And you multiply the electric field here by epsilon 0, epsilon r to find D in 2. So from this you can find D in 1. What is D in 1? It is epsilon 0, epsilon r times E1. And this one, D in 2, which is epsilon 0, E in 2. That one is easy. Minus grad with respect to y, it will be minus C1. And this one will be minus C3. You multiply by this, you find the D's. You put now D1 is equal to D2. D1 is equal to D2, where at the boundary where y is equal 0.8. That gives you the third condition. First condition, second condition, third condition. Okay? We still need one more condition, which is the equality of V also. When you find V here and V there, okay, V should be the same at the boundary. So also V1 is equal to V2 where at y equals 0.8 D. Okay? Look how many conditions we have here. We have this one, that one. That comes from V at y equals 0 is 0. This one comes from V at y equal D is 0. But remember, this is in medium 1, that is in medium 2. D is the same as the boundary between the two media. V is the same as the boundary between the two media. Okay? So you have 4 equations and 4 unknowns. Don't expect me to sit and solve this for you. You have to do the calculations and to obtain the answers which are given in your book on page 19 in the solution manual. Okay? Finally, you have to find the rho s. What is rho s at the upper and at the lower plate? That is the condition D equal rho s. Now you apply this at in medium 1, where at y equals to 0, that gives you rho s at y equals to 0. Having found D1, right, at 1, D in medium 1, set y equals to 0, and you can find rho s. And also you can find D in 2 at y equal D. That will be the value of rho s at y equal D. By this you can find rho s at the upper and the lower plates, and also the answers are given in your solution manual. My advice to you is always try, before you solve any problem, before you look at the lecture here, and before you look at the solution manual, try yourself to read the question, draw the figure, understand the figure, put the given on the figure, check how are you going to solve the problem, make a general plan, and then start your calculations. Okay? We can do another one, which is we did now 328. Now 329. Okay. Let me erase everything here and leave that figure only. Now we move to the another problem of boundary value problems, but the symmetry here is as you can see, is a cylindrical one. This is a coaxial cylinder, right? With inner electrode and outer electrode. The outer electrode is grounded, the outer one of radius B is grounded, the inner cylindrical conductor is, as you can see, held at a potential V0. The inner radius is A, outer radius is B. The region between the two is filled with charge of volume charge distribution K over R, right? K over R. You have to do what now? You have to solve in order determine the potential distribution in the region, solving the Poisson's equation. Even if he doesn't tell me that I have to solve Poisson's equation, I should know that, because here the region between the two conductors is filled with a volume charge density which is non-zero. So we have to solve Poisson's equation, which says that Laplacian of V is minus rho V over epsilon 0. Okay? Now, in order to do that, epsilon 0, if it is air, if it's in general any other dielectric, then you can keep it in general epsilon. Okay? So, this is a boundary value problem, number 1. The symmetry is a cylindrical one, so we have to use cylindrical coordinates. We have a volume charge density, so we have to solve Poisson's equation, and Laplace is 1. Since rho V is a function of R only, therefore we have, and this is a long one, double cylinder, therefore we have symmetry with respect to small r and with respect to z. So we have to apply the Laplacian where, in which coordinate system? In the cylindrical coordinate system, and we take only the variable to be r. Let me rewrite for you the Laplacian in cylindrical coordinates. Laplacian in cylindrical coordinates is the first term 1 over r partial with respect to r of r del v by del r Second term is plus 1 over r squared plus 1 over r squared del square v by del phi squared plus del square v by del z squared. So that's the complete Laplacian in cylindrical coordinates. But because we have symmetry with respect to phi and z, then this term here and that term there is 0. So this leaves me with what? With 1 over r partial with respect to r of r del v by del r is equal minus rho v over epsilon. That's rho v k over r minus k over r, and you have an epsilon here. Okay? Now since we are working between r equal a and r equal b, so we can multiply by r since r is different from 0. So we obtain the partial derivative with respect to r of r del v by del r is equal to minus k over epsilon. Okay? Now, since derivative with respect to r of this function is this, therefore r del v by del r is what? The derivative with respect to r is a constant, so the function itself is minus k over epsilon times r. Okay? K over epsilon times r. Okay? Fine. So now you can simplify the r's. It seems I have something here. 1 over r epsilon over r v1. Okay. So what is this now? This means that v is equal to minus k over epsilon times r minus k over epsilon times r plus c1 okay, the mistake is here. That is the derivative. Okay, so this will mean that del r del v by del r is equal minus k over epsilon r plus a constant c1. Now you divide by r, so you have del v by del r is what? Is minus k over epsilon minus k over epsilon plus c1 over r. Now you make another integral to find v, then your v will be minus k r over epsilon plus c1 ln r plus c2. So this is v now with two constants of integration. We have v equals to 0 at r equals to b. So this means that 0 equal minus kb over epsilon plus c1 ln b plus c2. v equals to v0 at r equal a means that v0 equal minus ka over epsilon plus c1 ln a plus c2. You can subtract now, you will remove the c2, obtain c1, and then substitute in one of them to find c2. Two equations, two unknowns. If you solve them, you will obtain a value of v, which is okay, so the value of v will be a minus k r over epsilon plus the c1 which you have obtained times ln r plus the c2 which you have obtained. This one and that one are obtained from the two equations of the two unknowns. Okay? You can, for example, having found v, you can do what now? You can find the electric field if you want E, which is minus grad v, and you have to apply this in cylindrical coordinates. And you can have rho s at the inner and the outer conductors. Remember, so rho s's will not be the same. Rho L here and rho L there would be equal and opposite in magnitude. Okay, so this is the problem 329. We are left now with one more problem of spherical symmetry on the boundary value problems, plus 2 or 3 problems on the method of images. We'll postpone this to the following lecture 28, and bye-bye for now.